the final idea today is to step away from looking for the so-called drawing, or by the way, designing drawing. Not design, at least not for the time being. Let's look at size. What should be the size of a pipe or a duct on a thing that moves, vehicle or animal? We know already that we're kind of we're digging for gold in the correct mountain here, because everybody knows that big animals have big blood vessels in a cross section. If you don't believe me, you go home, you do two things: you kill the cat, and then you kill a mouse, and you compare. So size, not shape. And here is the so-called duct. The duct, blood vessel, or duct that conveys this, back in my time, Freon, the fluid for the air conditioning system on an aircraft. It has a known mass flow rate. It has a length dictated by the size of the moving vehicle or animal, and then an unknown diameter. The question is simple, and you already know the technique because I posed this problem earlier, I think in the second lecture. I had the example of what should be the size of an area for a heat exchanger, which rides on the same moving thing, vehicle. That's obvious. Heat exchangers are many in your car. And animal, the internal surface of the lung is one. It's a mass exchanger. And then, as in all the other examples, the answer comes from answering the question, what is better for the mover? The mover is into, or actually the baby of a evolutionary process in the direction of greater economy, which means easier life, easier movement, smarter way to live. In this case, less power spent. And the power that every moving system, let's sketch the vehicle here. Here is the vehicle with the, this is a four-wheel thing, okay? And the pipe is sitting here, doing its thing in the engine. Same with the animal. I can sketch an animal and it's the same thing. And the power spent is due to two pieces of bad news. One is about pumping. Is the pumping power required by this m dot. And the other one is the power spent on carrying this duct full of its fluid. The blood in the animal is moving with the animal. That blood mass has weight. It has to be carried. And that weight better be the right weight. Remember Aristotle? Somewhere between too much and not enough. So this is to carry. And estimates for these two things are available. The pumping power is equal to m dot times delta P. and then divided by by the and I do this so-called penalty per unit length in every case. Per unit length. So length and then the density of the fluid in the pipe, and then the pump isentropic efficiency, which is basically 1, slightly less than 1. We have the formula for delta P. If you assume laminar flow, then you know the delta P varies as 1 over the diameter to power 4. If you go back in your notes of last lecture. So now I'm looking at the diameter for the blood vessel in the animal. Stay tuned, take notes, because there will be a aha at the very end. Sorry, my memories of a very loud aha at the very end. And then the other penalty divided by, per unit length is, I made this point graphically when I talked about the heat exchanger surface. The mover has a weight. Let's call it mass times gravitational potential, gravitational acceleration, and the proportional to that weight is the resistance that the ambient poses to the movement. It looks like some friction factor times the weight, but generally the resistance is not just the friction factor against the soil. It is the rubbing against the atmosphere. It is many other things, depending how if the movement is periodic, like in the case of running or flying. Things look complicated, but the formula doesn't change. And but the trick, or your secret, is that what is vertical on a drawing is proportional to what penalizes you, which is horizontal, and this force times the speed of the vehicle, that speed, is this second penalty. So if let's write it, mu mg and then speed. This time I'm talking about the mass of the pipe full of its fluid. That mass is the density of the fluid, and then the cross-sectional area, pi over 4 d squared, and then the length. But I divide by length, and so on the right-hand side, I have a penalty that varies as d squared. Meaning, if you do this correctly, and the analysis you can find in the textbook on page 120 in the DCT book, you find that the penalty, this W1, meaning the total, varies as a constant, which has a particular formula, divided by d to power 4, accounting for the first penalty, and another factor, C2, and then d to power 2. So if this is your problem, your pain, then the pain has two sources, and you can plot them versus d squared. The second one is rising linearly, This is Roman 2. The other one descends as a non-equilateral hyperbola. You know the story. There's an intersection. In this particular problem, the selectable d squared is not exactly the same as the location of the minimum in the curve that you don't know. But it's close enough in an order of magnitude sense, close enough for you to draw a few conclusions. And the formula that's derived exactly according to the minimization of the curve, and it's reported in the text, is the following, that corresponding to the minimum, so at the minimum, the optimal tube diameter should be 128. Don't ask me, you'll find why these constant factors appear. I'm just write them. And this mu, I defined it here. And then divided by pi squared, pump efficiency, fluid density squared. There's also the density of the wall. And then G and the speed of the vehicle, everything to power 1/6. That's what you get. So you read this thing, okay? I mean, I did, because I'm not a zoologist. Yes, Jack?
Where does the wall density come from?
The second one?
Yeah.
This is the density of the wall. Never mind, read the textbook, okay?
It's like the whole thing, there's no wall density.
Look, in engineering, unlike in animal design, where basically everything inside the animal has the density of water, okay? In engineering, the wall is more dense than the fluid that flows through it. You see, so
that's like from the weight of
the. That detail I omitted. If you want to forgive me, then you can put rho to power 3 here, okay? And say that you're talking about fish, where everything is really. In fact, everywhere in the animal realm is basically moving water trucks. That's what they are. That is what I am, you see. Incidentally, I get carried away, you see, make me be late here. Remind me to talk about the aquatic origin of the Homo sapiens. Yeah. So, questioning, does it make sense? Look, it does. Look, the bigger the flow rate, the bigger the tube. I began with that observation. These other things are kind of interesting. The faster the vehicle, the narrower the tube, even the more svelte the architecture. But one easy way to remember this discovery is that you should expect duct diameters to vary, to be diverse in proportion with the mass flow rate to power 1/3. Predicted And a few months after this problem-solving exercise, I was at a conference of biologists, and one of them showed the distribution of blood vessel diameters versus mass flow rate through the blood vessel on a log-log plot, and it was this way. And this was a cloud of data. And luckily I was sitting down, otherwise I would have fallen on the floor. I said, wow, here's the power of prediction, you see. I was not surprised because I had solved the problem unaware of, in fact, not interested in questioning whether what I'm doing is connected to anything. But it turns out that this so-called prediction is landed on fertile ground. In other words, feel free to pursue your own ideas, to try to find answers to your own questions. Before that, feel free to question your earlier conclusions or older ideas. Exhibit humility. That's another way to. Why? Because you may be wrong, but you may also be right. You see. So I'll see you on Wednesday.